Video that our electron and our, for example, electron antineutrino are not baryons. In other words, they're not made of quarks. Well, what we now need to do before we think about our fourth conservation law is think about what they are. Now, the way that we classify, for example, electrons and electron neutrinos is to say that they are leptons. You can see on the table, we've got a list of different leptons. There's the electron neutrino, the muon neutrino, tau neutrino, etc. And they've all got lepton number in that last column of 1. They've got different charges and different masses as well. Okay, leptons have lepton number 1. It then follows the anti-electrons or positron. And for example, an electron antineutrino or a muon antineutrino, anything with anti, has a lepton number of -1. Okay, so what we have here is the introduction really of, I suppose, 4 new particles and 2 familiar ones. Electron and electron neutrino being the familiar ones, and then the muon neutrino, the tau neutrino, all being perhaps a bit new. I think the key point here is that we're looking at different fundamental particles which are made of nothing else. Okay, and we're kind of looking at their different flavors. Okay, there's the electron, the muon, and the tau. And the key point being here, these are all very small particles which are made of nothing else, and they fall into this category of being a lepton. Now, why is the lepton number important? Well, as you may have kind of guessed, the lepton number is another thing that we must conserve when we're looking at any nuclear interactions or decays. So, okay, if we take our lambda becoming a proton plus a pion, you'll notice if we look at the lambda, the lepton number is 0, proton is 0, and pi minus 0. It's quite boring actually. 0 is equal to 0 plus 0. Okay, so in some cases, whenever you're dealing with hadrons, so that is things made of quarks, they're going to have a lepton number of 0 because there's no leptons inside them. Okay, so in this case, this is fine because the lepton number is conserved. We've not suddenly produced an electron from somewhere or an antineutrino. If we have a lepton number of 0 on the left-hand side, then it must also be equal on the right-hand side. Okay, well, this has got to apply to our other decay as well, which was our neutron becoming a proton and an electron antineutrino. And hopefully this time we'll see something slightly more different. Okay, what you'll notice here is, again, my neutron, which is a hadron, it's made of quarks, has a lepton number of 0. The electron is a lepton, and so therefore it has a lepton number, of 1. Our proton has a lepton number of 0. I jumped past that one. And then we've got an electron antineutrino. Well, the antineutrino has a lepton number of -1, and so therefore 0 is equal to 0 again. And again, as with the previous example, we're not always going to have 0 on the left and 0 on the right. It just happens that this decay has that particular pattern. Okay. The key point here really is that sometimes students have to think of a way of remembering what goes with what. So in this beta minus decay, this is the neutron becoming a proton, we produce a lepton. And the question is often, well, why does that produce an antineutrino? And really it's to do with our conservation laws. It produces an antineutrino because an antilepton has to be produced in this decay in order to balance out those lepton numbers. In other words, in order for the 0 lepton number on the left-hand side to be conserved, we must have an antineutrino as opposed to a neutrino being produced on the right. So again, our lepton number has to be conserved in all interactions.